Every time a card is swiped anywhere in the world, something has to decide in a few thousandths of a second whether that transaction is fraud. And to decide, the model needs to know things. How many times this card has been used in the last hour, how far this shop is from the last one, whether this amount is normal for this cardholder at this kind of merchant. Roughly 200 facts like that. And the model cannot work any of them out at the moment of the swipe because there's no time. They have to already exist. So somebody has to compute 200 facts for 500 million cards from 2 billion transactions a day. Every day. That is the job we follow for this entire series. And today we start with the simplest question. Why can one computer not do it? A card being swiped at a terminal with a clock showing milliseconds, and behind it, a warehouse of stored files labeled 2 billion swipes yesterday. Yesterday's swipes come to about 400 gigabytes, with about a year of history behind that. Your laptop has 16 gigabytes of memory, so the obvious thought is that the data does not fit. True, but not the interesting problem. You could read it in pieces, load a chunk, process it, discard it, load the next. The interesting problem is time. Reading 400 gigabytes once from storage at a few hundred megabytes a second takes somewhere around a quarter of an hour. That is before any actual work. And you're not reading it once. Computing spend over 90 days means going back through months of it. A fresh 2 billion rows arrive every day, and the whole thing has to finish before the next batch lands. One machine does not fail because the data is too big. It fails because it has one of everything. One set of processors, one memory bus, one connection to storage. Everything queues. A single computer with a long queue of data chunks waiting to enter it, labeled one processor, one pipe, everything queues. There are two ways out, and only one works. The first is a bigger machine, more memory, more processors. That genuinely helps right up until it doesn't, because there's always a biggest machine you can buy. It costs an absurd amount, and 2 billion rows a day will eventually walk past it. The second is many ordinary machines at once, which sounds obvious and runs straight into a problem people do not expect. Pause the video and think about it. You have 100 machines and 400 gigabytes of data. What has to happen first? 100 small machines on one side and a 400 gigabyte block of data on the other with a large question mark between them.
The data has to reach the machines, and that is the trap. If you keep the data in one place and ship it out to 100 workers, you have invented a slower version of your original problem because every byte now crosses a network before anything happens to it. Networks are far slower than a local disk. You would spend all your time moving data and almost none processing it. So the whole design inverts. You do not bring the data to the code, you send the code to the data. This is the idea underneath everything else in this series. The instructions are tiny, a few kilobytes. The data is enormous. So you leave the data where it is, split across many machines, and post a copy of the instructions to each. Tiny envelope labeled Your Code, a few kilobytes, being posted out to many machines, each sitting on a large block of data labeled Stays Put. For that to work, the data has to be broken into pieces. Spark calls those pieces partitions, and when it reads files, it chops them into chunks of a size you configure. We will use 128 megabytes throughout this series, a common setting, but treat every number here as our setup rather than a universal truth. 400 gigabytes cut into chunks that size gives you roughly 3,200 partitions, not files, not rows. Partitions. And this is the unit that matters because a partition is the amount of data one worker chews through at a time. One honest note for later. How your files are laid out in storage strongly influences how Spark splits them, and the word partition ends up meaning two different things depending on whether you mean files on disk or work in memory. That confusion is expensive enough to get a whole episode of its own. For now, partitions are chunks of work. A 400 gigabyte block being sliced into a long row of small equal chunks labeled 3200 partitions of about 128 megabytes. Now the machines. The processes that do actual work are called executors. Say 100 of them. Each has its own memory and, importantly, several processor cores, 4 each in our setup, though real clusters vary enormously. So each executor can work on 4 things at once. 100 executors with 4 cores gives 400 slots, 400 pieces of work at the same time. A single piece of work, one partition processed by one core, is a task. That is the atom of everything Spark does. One task, one partition, one core. 100 executor boxes, each showing 4 slots, with the arithmetic 100 executors times 4 cores equals 400 tasks at once. So our job becomes 3,200 tasks running 400 at a time, in waves. 8 waves, and the pass is done.
Who organizes all this? One more process, and it does not touch your data at all. It is called the driver, and it runs your actual program. It works out what needs doing, breaks it into tasks, hands them to executors, tracks which have finished, and hands out more as slots free up. The distinction matters more than it sounds. The driver holds the plan. The executors hold the data, and one command breaks that rule deliberately. It is called collect, and it does what the name says. It gathers every row from every executor back to the driver. On a small result, useful. On 400 gigabytes, it funnels the entire dataset into one process, never sized to hold it, and the job dies with an out-of-memory error that looks mysterious until you know this. If you remember one word from this episode, make it that one. A driver box handing tasks to executors that hold data, and beside it, every executor funneling its data back into the driver, which is bursting, labeled collect. Everything comes home. Now, here is a consequence that catches people out, and it follows directly from what we just built. Your parallelism is limited by your partitions, not your cluster. 400 slots available, but the data split into only 10 partitions gives you 10 tasks. 10 cores work, 390 sit idle, and your expensive cluster runs at 2.5% of capacity. People hit this constantly. They add machines and nothing gets faster because the data was never divided finely enough to use them. A cluster where only 10 of 400 slots are lit up and working, the rest grayed out, labeled 390 cores doing nothing. The opposite is also a problem. Split into a million tiny partitions, and you spend more time scheduling and tracking tasks than working. Every task has overhead. Too few waste the cluster, too many drowns you in bookkeeping. So here's the big picture. One machine cannot do this because it has one of everything and everything queues. Many machines can, but only if you stop moving data and start moving code. The data is split into partitions, executors run tasks on them, one task per partition per core, and a driver hands out work without touching the data itself. A summary strip reading split into partitions, then send code to each, then tasks run in parallel, then driver coordinates. Now, you might reasonably assume that when you write your job and press run, all of that machinery immediately springs into action. It does not. You will write 5 lines of code, press run, and Spark will do nothing at all for a couple of seconds. Then, everything will happen at once and not in the order you wrote it. That is not a bug. It is the second most important idea in the whole system, and it is next time.